Imagine a planet twice the size of Earth, covered in a global ocean hundreds of miles deep, all tucked under a thick, suffocating shroud of hydrogen gas. These are not Earth 2.0. These are Hycean worlds, a newly defined class of habitable exoplanets that might be our best chance at finding alien life within the next decade. With the James Webb Space Telescope, JWST, already sniffing their atmospheres for signs of biological activity, we are standing on the threshold of a discovery that could change our understanding of our place in the universe forever. For a long time, the Goldilocks Zone was all about finding rocky planets like Earth, but a new frontier has emerged: Hycean worlds. The name itself is a portmanteau of hydrogen and ocean. These planets are typically sub-Neptunes, worlds larger than Earth but smaller than Neptune, and they appear to be incredibly common throughout our galaxy. Unlike Earth, which has a thin nitrogen-oxygen atmosphere, Hycean worlds are wrapped in hydrogen H-2, which acts as a powerful greenhouse gas. This allows them to maintain liquid surface oceans, even when they are far away from the traditional habitable zones of their parent stars. A Hycean world is defined by a specific set of conditions: a hydrogen-rich atmosphere in direct contact with a massive liquid water ocean. This is a crucial distinction from planets like Neptune. On giant gas planets, the internal pressure is so high that water exists in exotic, supercritical phases rather than a life-friendly ocean. Hycean worlds are the just right size, typically between 1.6 and 2.6 times the radius of Earth, to maintain a stable liquid surface where chemistry can lead to biology. One of the most exciting candidates is a planet called K2-NeB. Located 120 light-years away, this planet sits comfortably in its star's habitable zone. Observations from the Hubble Space Telescope first detected water vapor She2O in its atmosphere, and recent data from the James Webb Space Telescope has confirmed the presence of methane CH4 and carbon dioxide CO2. These chemical markers suggest that underneath that thick hydrogen veil, a massive ocean is waiting to be explored. How do we find life on a world we can't visit? We use the James Webb Space Telescope's infrared spectrographs to study the light passing through the planet's atmosphere. We are looking for biosignatures, gases that, on Earth, are primarily produced by living organisms. On a Hycean world, one of the most anticipated biosignatures is Dimethyl Sulfide, DMS. On Earth, the only significant source of DMS is life, specifically phytoplankton in our oceans. If the JWST detects a strong signal of DMS on a planet like K2-18b, it would be a smoking gun for biological activity. Other indicators include methyl chloride, a CH3 and nitrous oxide N2O. When these gases are found alongside methane and carbon dioxide, they create a chemical disequilibrium, a state where the chemistry of the atmosphere doesn't make sense unless something active, like life, is constantly pumping those gases into the air. We also look for other molecules like ammonia NH3 or acetylene CH2, which can help define the chemical kinetics of these distant worlds. However, being a Hycean world isn't a guarantee of life. These planets face unique geochemical challenges. Because their oceans are so incredibly deep, the pressure at the bottom can become so intense that the water turns into exotic forms of high-pressure ice, like ice the Severe or Ice X. This creates a thick barrier that separates the liquid ocean from the rocky mantle below. On Earth, the interaction between water and rock is vital. It delivers essential minerals and nutrients to the ocean through hydrothermal vents. If a Hycean ocean is bottled up between hydrogen above and ice below, life might struggle to find the raw materials it needs to survive. There is also the issue of atmospheric stability. Small planets close to active stars can have their hydrogen atmospheres stripped away by intense stellar radiation over billions of years. For a Hycean world to remain habitable, it must be large enough to hold onto its hydrogen but small enough not to turn into a mini Neptune with no solid or liquid surface. Despite these challenges, Hycean worlds represent a massive shift in how we think about the universe. We are moving away from an Earth-centric view of habitability. By expanding our search to include planets with hydrogen atmospheres and deep oceans, we have exponentially increased the number of places where life might exist. Because these planets are larger and have puffy atmospheres, they are much easier for our telescopes to characterize than small, rocky Earth analogs. The discovery of Hycean worlds has opened a new door in the search for our cosmic neighbors. Whether it is the vast, dark oceans of K2-80b or the potential habitats on countless other sub-Neptunes, we are closer than ever to answering the ultimate question: are we alone? As the James Webb continues to beam back data using its near, infrared and mid-infrared instruments, we might be just one spectrum away from a historic revelation. If you enjoyed this journey to the ocean worlds of the deep galaxy, make sure to subscribe and turn on notifications so you don't miss our updates on the latest JWST discoveries. What kind of life do you think could survive in a hydrogen-rich ocean? Tell us your thoughts in the comments below!